What is up, everyone? It's Miss Wesley. I hope you're as excited to be here as I am. We are talking integral applications in a new unit now, chapter 6, and I'm looking at a packet called the volume packet. And that'll be the main application we get to in this unit, but we'll start by expanding upon the area that we had been calculating using definite integrals in the previous units. We'll start on page 1 here. As we get this ready to go, here's your joke for the day. My wife asked me for some lipstick, but I passed her a glue stick instead. She hasn't talked to me since. What does it say here, and do you recognize this concept? Area of a region between two curves. The area of a region bounded by the curves y equals f of x, you see it in this picture up top, we can call that the top function, and y equals g of x, the bottom function. And the lines x equals a to x equals b, where f and g are continuous, no gaps or skips, and f of x is on top of g of x in the entire region. It's bounding the shaded region from the top. So let me shade that on the picture here. We're talking about this entire shaded area between y equals f of x and y equals g of x. And what we had seen a hint of before when we tried a couple problems like this was that you take a definite integral from x equals a to x equals b of the top function, that nickname is f of x, minus the bottom function. Gave us a good answer. Taken with respect to x, I'll put top function for f of x, and we'll say bounded by the bottom for g of x. And that's what you'll see in the first few examples that we're going to try. And I'd like to not only use the definite integration to find the area, I want to picture the area as well. These problems are much more straightforward if you can see the graph. We'll use a combo of graphing by hand methods and maybe just reach into the graphing calculator sometimes when we hit a function where we need a little bit of help. It says find the area of the region bounded above by y equals e to the x. Can we put that on our picture first? And I'm going to try to do my best to make this look neat, and I hope you do the same. So what are some easy powers we could raise e to? We can raise anything to the 0 power and get 1. So you have an anchor point at 0, 1. E to the first power, do you know an estimate? It's about 2.71828. And there's exponential growth from there. It's never going to come down and hit the x-axis. I think in this problem it actually doesn't matter what it's doing over in quadrant 2. But quadrant 1 is pretty important. You get a smooth exponential growth curve hitting an asymptote from down below. So this is y equals e to the x. Okay, it's also bounded below by y equals x. Can we get a straight line on this picture? Going diagonally up, it has the points 1, 1, 2, 2, 3, 3, and so on. It'll go right through the origin. Almost miss it there. Y equals x. So above by the red graph, below by the blue graph, and it even tells us where it's bounded on the sides. Bounded on the sides by x equals 0 and x equals 1. Well, x equals 0 is already drawn. It's the y-axis. X equals 1 is this vertical line here. I want to shade the region in question, and I'll do that here. Let me just move myself out of the way. The region in question is going to be between these 4 lines and curves. That's the area we want to find. Okay, I think this is one we can easily integrate to. So area is going to equal, sometimes we'll just put capital A for area, a definite integral from one x value to another. And we were kind of nicely gifted those two values in the problem, from 0 to 1 sideways. What function bounds the shaded region from the top? Well, e to the x, the red graph. So e to the x is your top function minus what function bounds the region from the bottom, y equals x. It's important that both of these equations are solved for y so that you have easy x expressions, easy expressions in terms of the variable x for which to integrate this expression. So if you want, you can give yourself a note there. This is the top function, like the rule says, minus the bottom function. And I think there's nothing left to do but work our magic, take a definite integral. So integral of e to the x might be my favorite thing to integrate because I don't have to do anything to it, e to the x, minus the integral of x squared over 2. Evaluated from 0 to 1, go ahead, do your plug-in, e to the first minus 1 squared over 2, minus e to the 0, which is not 0, minus something that is 0, 0 over 2. So this should give you what? E minus a half minus the number 1. Anything to the 0 power is 1 plus 0, so that's not going to make much of a difference. Exact value answer, e minus 1.5 square units. It's a weird way to leave the answer for just the common lay person, so we will put that into the calculator, get a rough approximation, 1.218 when you're rounding to the nearest thousandth units squared. Check back with the picture, make sure it looks like that's a reasonable estimate for the amount of units that would be enclosed there. But yeah, just between 1 and 2. All right, let's see if we can find some more top and bottom function action in the second question. Find the area of the region. Now this time they didn't give us, like last time they said specifically, your integral for area is going to go 0 to 1. I don't see that here, so maybe the graph can help us see where our limits of integration will be in this one. Let's graph both of these functions. So you've got y equals x squared. That is your classic parent graph parabola. If you want to show a few points on it, it might be helpful for what we're about to try. Right? When you square 1, you get 1 back. When you square 2, you get 4. So you get a nice parabola, yikes, curve from there. Not my prettiest. This is y equals x squared. And the other one, is this also a parabola? It should be, right? Parabola that opens down because you see that negative coefficient in front of the x squared term. So it's going to be something like this. I'm going to use a little bit of pre-calc down here to see if I can get things like x-intercepts and a vertex of this parabola. So for this parabola, let's get the x-intercepts. We know you can get that by hand by setting the expression equal to 0. So 0 equals 2x minus x squared. Just finding the x-intercepts. We can get them by factoring. Take a GCF. You get x, is this 2, because I pulled an x out, minus x, and set both parts equal to 0. So you have x-intercepts at 0 and at 2, the two solutions to that equation. So I'll just put red dots here and here. I know the parabola is going to open down from there, and I can kind of see conveniently where it's going to fall now. I could also go in and calculate the vertex. What I really care about, let me just sketch it in here, rough sketch for now just to get my bearings. What I really, really care about, again, are those two intersection points. If I know where the two graphs hit each other x-wise, and it looks like it's going to be around 1, that's my guess, then I'll have easy answers for what I should put for those limits of integration. So put this work underneath just in case we hit a problem that's going to be a little bit trickier algebraically. Let's do the intersection point calculation off to the side. Intersection points. Okay, so that was kind of nice. We found the x-intercepts. That's fine. What's more important, we want to see where these two curves hit one another, where those two graphs hit each other. So it's as if you're solving a system when you're finding intersection points. If you have a y equals this and a y equals that, you can set the two x expressions equal to one another and see what you get. So I get x squared. I want to find out where x squared would equal 2x minus x squared. Pick a side to move everything to in this quadratic equation. I'm thinking maybe the left-hand side to keep the leading coefficient positive. So how about add x squared to this side? You get 2x squared, and subtract 2x from both sides. And now let's factor again. Let's GCF. So 2x comes out, and x minus 1 is left over. In terms of x, the two intersection points are at 0, which we knew about. They hit each other at the origin, and 1, the one that we had guessed. So you have these two intersection points at 0, 0, and it wasn't too hard to find or guess that the other one was going to be at 1, 1. A bit more work that you see down here in colored pen than we had to do in the last one, because again, the last one just told us go from 0 to 1. But now all that hard work gives us that this integral sideways, x values, is going to be an integral of the region enclosed between these two curves from the x value 0 to the x value 1. So those can be your limits. All right, so now I got to follow the model we set up the last time. Last time we set up this integral so that it was the top function minus the bottom function. Well, which is which? It looks like the red upside down parabola bounds the region from the top. So let's put that first. Let's go top function, 2x minus x squared, minus bottom function, which happens to also be x squared. Top minus bottom. Look, okay? Let's simplify and then integrate. You're going to integrate eventually from 0 to 1. What are you integrating? Let's get this in the right order. Negative 2x squared, if we combine those like terms, plus 2x, taken with respect to x. Okay? We'll take an integral and we'll do the plug-in. So integral comes next, negative 2 over 3 x to the third, plus 2 over 2, so just 1 x squared, evaluated from 0 to 1, and we can leave this as a fraction or decimal, whichever you prefer. 1 gets plugged in, so negative 2/3 times 1, plus 1 squared, so plus 1, minus, now 0 gets plugged in, but like many times, I don't think you're going to have much, minus 0 again. So we'll just say minus nothing. Negative 2/3 plus 1 gives you exactly 1/3 of a square unit of area. And that does look like, there's only a little sliver there in the picture. It does look like it makes sense in the context of the problem. Third one, final one on the page. I want to think about a cool strategy with you guys, and you're going to see trig comes into play in this question. So you have a little picture here. We don't have to graph it for ourselves. Here is, if you think back to when you were graphing sine and cosine, a graph of the cosine wave and a graph of the sine wave. And we see that they're hitting each other at x equals pi over 4 is where they intersect. And what we want to find is the area of both shaded parts of this region. So this part and this part added together. And I want to talk about two strategies for finding this and eventually use the quickest way we know how. There's a little problem with doing this. I'm going to write something that I don't know if we're going to use. Technically, the entire region goes all the way from 0 to pi over 2. So why can't I set up the integral this way? An definite integral from 0 to pi over 2 of top minus bottom taken with respect to x. What's the problem with that? Well, is one function always bounding the region from the top? And the answer is no. The functions crisscross at the point x equals pi over 4. So at one point, cosine's the top function, and then they flip-flop, so it becomes the bottom. So there's no way to calculate this integral as one definite integral. Instead, we'll find this area. I'll put a equals again for area. In two separate parts. So one strategy, I'll just start this as one option, would be to go, okay, so from 0 to pi over 4, what function's on the top? So cosine starts as top, and then it switches to the bottom. So this is cosine minus sine dx. And I could add the integral from pi over 4 to pi over 2 of now they flip-flop. So now, what is it? Sine is on the top, and then cosine's on the bottom. Sine of x minus cosine of x. I just think that's going to take a lot of time. And when I look at the picture and I think of the symmetry of trig graphs and the relationship between cosine and sine, maybe you're already thinking of a quicker way. Let me say or. Can we do this just by calculating one integral? So I'll say or here. I could go integral from just, let's say, 0 to pi over 4 of, I'll start with this first region where cosine is the top function and sine is the function that's underneath, the bottom function. And what would you do to this so that it would add both areas? Well, they're symmetrically the same. Let's just double. If you double this one area, you will get the total area of the two added together. So we're kind of cutting the work in half, just one integral to take. Let's try it. Leave the constant outside. Just leave the two, take your integral separately. We need the integral of cosine of x. So a function whose derivative is cosine, that would be sine. So we'll say sine of x. Minus the integral of sine of x, which is actually negative cosine. Let's change this into a plus sign. Minus negative cosine plus cosine of x taken with respect. And actually we just took the integral, so I'll get rid of the dx. Instead, evaluate from 0 to pi over 4. Okay, so plug-in time. We've got 2, right? We've got the sine of pi over 4 plus the cosine of pi over 4. Minus, now I have to subtract those expressions with 0 plugged in. Sine of 0 plus cosine of 0. And that's just a 0 there. Let's just see what we remember exact value-wise. Okay, so I'll leave the 2 completely on the outside. And I'll say sine of pi over 4. What do you remember? Exactly, it's square root of 2 over 2. Feel free, at the end of this, we might just use a decimal approximation anyway. But this is what we learned as an exact value. Plus the cosine of pi over 4 happens to be the same thing. So it's square root of 2 over 2 minus, what's the sine of 0? So sine of 0 is 0, and the cosine of 0 is going to be 1. Okay? You could get an exact value as 2 square root of 2 minus 2. I'd prefer probably just a decimal approximation. Go ahead and type it in. You get to the nearest thousandth, 0.828 square units. So symmetry pretty much helped us out there. There was only one integral to take. If we had gotten just the integral from 0 to pi over 4, we'd have half of that. Doubling it solves our problems there for a second. Hope you enjoyed. Talk to you soon. Keep up the good work. Signing out.